Hello students, so welcome back to my video lectures on multiple choice questions from the third chapter. What is that? Okay, classification of elements and periodicity in properties. Okay, so students, I think we have solved so many problems. Okay, I think we have solved up to 10 questions in the first lecture. Okay, then we now in this video lecture also we shall continue with the same lecture series. Okay, yes, so we have finished I told you that we have finished 10 questions, isn't it? Okay, so which of the following is not an actinoid? It is, okay, exactly terbium, because actinoid starts from 88, okay, and lanthanoid starts from 57. Terbium is a lanthanoid, it's not an actinoid. I have told you that. Okay, yeah, next question. Elements belonging to the same group of periodic table have, okay, yes, elements belonging to the same group of periodic table have same number of energy levels, same number of valence electrons, same number of electrons, and same ionization enthalpy. So elements belonging to the same group of periodic table have what? Okay, let us take one group of elements, a set of one group elements. Okay, for example, I will consider first group 1 elements. Which are the group 1 elements? Yeah, group 1 we have lithium, okay, sorry, sodium, potassium, rubidium, cesium, and francium. Is that correct? Okay, lithium, sodium, potassium, rubidium, cesium, and francium. Atomic number of lithium is 3, 11, 19. Is it correct? Okay, so 19 plus okay, yes, 11 plus 8 is 19, 19 plus 18 is 37, isn't it? 37 plus okay, 18, 37 plus 18 is how much? 55. Okay, 55 plus 32 is, okay, 87. Am I correct? Let us check. Okay, yeah, yes, lithium 3, 11, 19, 37, 55, 87, exactly. Okay, yes. Okay, so now let me write the electronic configuration of these elements. So if I take lithium, its electronic configuration is 1s2, 2s1. Is it correct? Okay, sodium 1s2, 2s2, 2p6, 3s1. Potassium 1s2, 2s2, 2p6, okay, 3s2, 3p6, okay, 4s1, isn't it? 4s1, okay, correct. Rubidium 1s2, 2s2, 2p6, 3s2, 3p6, okay, 4s2, yes, 3d10, 4p6, 5s1, okay. So like the cesium, yeah, 1s2, 2s2, 2p6, 3s2, 3p6, etc, 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 6s1. Okay, francium same, okay, yes, last it will end with what? 7s1. Okay, these elements belong to the same group, that is group 1. Is that correct? Okay, these elements belong to the same group. Which group? They belong to group 1. Okay, they belong to what? Group 1, and they are called as alkali metals. I hope you know this. Now observe the electronic configuration of these elements which belong to the same group. For lithium, 1s2, 2s1, okay, 1s2, 2s2, 2p6, 3s1, like that, 4s1, 5s1, 6s1, 7s1. Now just observe the valence electronic configuration of these elements which belong to the same group. Okay, yes, so for lithium, 2s1, for sodium, 3s1, potassium, 4s1, rubidium, 5s1, okay, cesium, 6s1, for francium, it is 7s1. Okay, that means elements belonging to the same group, they have same number of electrons in the valency shell. Okay, yes, correct. Yeah, lithium has 1 electron in its valency shell, sodium has 1 electron in its valency shell, okay, potassium has 1 electron in its valency shell, rubidium has 1 electron in valency shell, cesium has 1 electron, okay, francium has 1 electron in its valency shell. So that means the conclusion is, you take any elements, you take elements belonging to any group. Okay, if the elements belong to the same group, then those elements will have same number of electrons in the outermost shell. Okay, they have same number of electrons in the outermost shell or valency shell. Got it? So you should remember, elements belonging to the same group will have same number of electrons in the valency shell. Okay, so what is the correct answer? Elements belonging to the same group of, okay, the periodic table have same number of energy levels? No. Same number of valence electrons? Yes. So okay, that's correct. Then option B, same number of valence electrons. Same number of valence electrons. Are we clear? Yes, it's option B, exactly. Okay, now let us move to the next question. So you can take any group. Okay, remember this. So this is first group. First group has 1 electrons in its valency shell. Second groups will have 2 electrons in their valency shell. Okay, third group will have 3 electrons in valency shell, 4 electrons in valency shell, 5 electrons, 6 electrons, 7 electrons. Okay, like that it goes. Okay, 13th group again has 3 electrons in valency shell, 14th group 4 electrons, 15th group 5 electrons, 16th group 6 electrons, 17th group 7 electrons, 18th group has 8 electrons in their valency shell. Okay, so elements belonging to the same group will have same number of electrons in the valency shell. That's exactly correct. Okay, yes, next question. Okay. The question says, the element in which the electron are progressively filled in 5f orbitals are called. The elements in which the electrons are, okay, progressively filled in 5f orbitals. See, if the electrons are filled in f orbitals, okay, if the electrons are filled in f orbitals, then we know they are f block elements, isn't it? Okay, f block elements. Say yes or no. Okay, if the electrons are filled in f orbitals, let it be filled in any f orbital. Okay, if the electrons are progressively filled in f orbital, they are called as f block elements. Just now we understood, in the previous video we understood, f block elements, okay, has 2 series. One is lanthanoid series, and the other one is called as actinoid series, isn't it? Actinoid series. Okay, lanthanoid series and actinoid series. Please remember, it's a direct question. In case of lanthanoids, 4f orbital is progressively filled, whereas in case of actinoids, 5f orbital is progressively filled. Okay, in case of lanthanoids, 4f orbitals are progressively filled, whereas in case of actinoids, 5f orbital is progressively filled. So the question, okay, what is it? The elements in which the electrons are progressively filled in 5f orbitals are called as, are they lanthanoids? No. Are they actinoids? Yes, they are actinoids. Okay, are they transition elements? Transition elements are nothing but, okay, d block elements. No, for d block elements, okay, d orbitals are progressively filled. Halogens are p block elements. For p block elements, okay, p orbitals are progressively filled. But the question is very clear. 5f orbital, that means f orbitals are filled. If their f orbitals are filled, then they are f block elements. Okay, for f block we have 2 series, lanthanoids and actinoids. For lanthanoids, 4f orbital is filled. For actinoids, 5f orbital is filled. 5f orbital is filled. Okay, hope there is no doubt. Okay, let me pass on to the next question. Yeah. Which of the following will have lowest electron affinity? Yeah, okay. Which of the following has lowest electron affinity? Lowest electron affinity. So we have nitrogen, oxygen, argon, boron. Okay, so we have, if you arrange them strictly according to the periodic table in the increasing order of atomic number. So first comes boron, and then comes carbon, nitrogen, oxygen, fluorine, okay, neon. After neon there will be argon. Okay, yes. So boron, carbon, nitrogen, oxygen, argon, okay, sorry, fluorine, neon and then argon. So we have got nitrogen, oxygen, argon and boron, isn't it? So what happens to, what was the question? The question is which of the following will have lowest electron affinity? Lowest electron affinity. We know as we go along the period, okay, as we go along the period, okay, from left to right, electron affinity increases, isn't it? Along the period, electron affinity increases. Am I correct? Okay, along the period, electron affinity increases. That means, okay, fluorine has more electron affinity than oxygen. Oxygen has more electron affinity than nitrogen. Nitrogen has more electron affinity than carbon. Carbon has more electron affinity than, okay, boron. By the way, what do you mean by electron affinity? What is electron affinity? Okay, it is the amount of energy released when an electron is added to an isolated, okay, gaseous ground state atom. Isolated gaseous ground state atom. It is the amount of energy released, okay, when an electron is added to an isolated gaseous ground state atom. For example, for fluorine, if I add one electron, it forms fluoride ion, along with which heat energy is liberated. Okay, heat energy is liberated. The amount of energy that is released when an electron is added to an isolated gaseous ground state atom is called as what? Electron affinity. Okay, as we go along the period, electron affinity increases. That means, okay, so more and more amount of an electron affinity increases means more amount of energy is released as we go along the period. So fluorine has more electron gain enthalpy than oxygen, and then nitrogen, then carbon, then boron. How about noble gases then? I am not talking about noble gases here. I just told you that fluorine has more electron gain enthalpy, electron affinity than oxygen. Oxygen has more electron affinity than nitrogen, then carbon, then boron. How about noble gases? We know noble gases have, okay, stable configuration, isn't it? They have stable configuration. What is that stable configuration? Okay, stable configuration of NS2, NP6. They have a stable configuration of NS2, NP6. Okay, we also know very well that it is difficult to remove the electron, and also it is difficult to add an electron from a stable configuration, isn't it? From the stable configuration, it is difficult to remove the electron, as well as it is difficult to add an electron. That means to say, for these noble gases, it is difficult to add an electron. If it is difficult to add an electron, how about the electron affinity? Electron affinity will be very, very, very less. Okay, if it is easy to add an electron, then electron affinity will be more. If it is difficult to add an electron, then electron affinity is least. Okay, I hope it is clear. Any doubts with this? So for all these elements, okay, electron affinity, okay, for all these elements, that is from boron to fluorine, electron affinity is negative. Whereas for noble gases, electron affinity is positive. Okay, for noble gases, electron affinity is positive. For other elements, electron affinity is negative. So understand one point. Okay, it will be very difficult to remove an electron, and also it will be very difficult to add an electron to a stable configuration. Hence, can I say that electron affinity of noble gases is least? Yes, obviously. Okay, I just told you electron affinity for noble gases is positive, whereas for other elements it is negative. So according to the question, which of the following will have lowest electron affinity? Is it nitrogen, oxygen or boron or argon? Yeah, it is argon, because argon is a noble gas. It has already a stable configuration. It will be very difficult to add an electron to a stable configuration. Therefore, electron affinity of argon is least. Okay, is that simple? So the answer is option C. Okay, yeah, let me move on to the next question. Let me move to the next question. The next question says, yeah, okay. Which of the following arrangement represents the correct order of electron gain enthalpy? Okay, which of the following arrangements represents the correct order of electron gain enthalpy? Okay, is talking about electron gain enthalpy, isn't it? Electron gain, okay, enthalpy. Okay, yes. So what happens to electron gain enthalpy along the period? Just now we spoke about it. Electron gain enthalpy is nothing but what? Electron affinity. They are one and the same. Electron gain enthalpy is nothing but electron affinity. So what happens to electron gain enthalpy or electron affinity along the period and down the group? Okay, yes, we know along the period ionization enthalpy, electron gain enthalpy, electronegativity increases. Okay, whereas down the group ionization enthalpy, electron affinity and electronegativity decreases. Down the group it decreases. Now they have given 4 elements: oxygen, sulfur, fluorine and chlorine. Okay, if you arrange them strictly according to the periodic table, first you will have oxygen family and then halogen family, that is fluorine. Okay, below oxygen you will have sulfur, below fluorine you will have chlorine. Okay, below fluorine will have chlorine, is it correct? Okay, oxygen, sulfur, fluorine, chlorine. So along the period electron affinity increases. Down the group electron affinity decreases. Is that correct? Okay, so that means as we go from oxygen to sulfur, electron affinity should decrease. As you go from fluorine to chlorine, electron affinity should decrease. But if you go from oxygen to fluorine, electron affinity should increase. If you go from sulfur to chlorine, electron affinity should increase. Understand the point? Okay, simple. Okay, as you go along the period, electron affinity increases. As you go down the group, electron affinity should decrease. So what is the correct answer then? So according to this, okay, so as you go from oxygen to sulfur, it should decrease. Oxygen to fluorine, it should increase. Fluorine to chlorine, it should decrease. Isn't it correct? Okay, so that means, yeah, fluorine should have more electron gain enthalpy than chlorine. Chlorine should have more electron gain enthalpy than oxygen. Oxygen should have more electron gain enthalpy than sulfur. Okay, this should have been the correct way, because along the period, okay, electron affinity will increase. Down the group, electron affinity will decrease. So from oxygen family to halogen family, okay, halogen family has more electron gain enthalpy than oxygen family, obviously. Okay, they have more electron gain enthalpy than oxygen family, because electron affinity should increase along the period. Okay, but as you go down the group, electron affinity should decrease. So, okay, my analogy is fluorine should have more electron gain enthalpy than chlorine. Chlorine should have more electron gain enthalpy than oxygen. Oxygen should have more electron gain enthalpy than sulfur. But this is exactly wrong. It is exactly wrong. It is absolutely wrong. Okay, understood? Are you getting my point? Okay, so this order is wrong. That means there is an exception here. There is an exception. So we have, again, let me write oxygen, sulfur, fluorine, chlorine. As am I telling you, okay, as you go from oxygen to sulfur, okay, electron affinity should decrease, isn't it? As you go from, okay, fluorine to chlorine, electron affinity should decrease, because down the group, okay, now yes, electron affinity should decrease, isn't it, according to the rule. But what is going to happen here is, Chlorine has more electron gain enthalpy than fluorine, or chlorine has more electron affinity than fluorine. Sulfur has more electron affinity than oxygen. Why? Okay, chlorine has more electron affinity than fluorine. Sulfur has more electron affinity than oxygen. Why? Why is it? Why is it? Because of small size of fluorine. Okay, how many electrons are there in fluorine? 9. How many electrons are there in oxygen? 8. Okay, because of small size of fluorine and because of small size of oxygen, okay, if you add one more electron to this fluorine, okay, what is electron affinity? It is the amount of energy released when an electron is added. So if you add an electron to this small sized fluorine, okay, there will be more repulsion. That means it is difficult to add an electron to fluorine when compared to addition of electron to chlorine. Okay, so in chlorine, okay, the size increases. As the size increases, repulsion will decrease. Okay, so chlorine, so it is quite easy to add an electron to chlorine than adding an electron to fluorine. In fluorine, okay, because of small size, there will be more repulsion. Okay, whereas in chlorine, since the atomic size increases, there will be less repulsion. Okay, and the same reason holds good for oxygen and sulfur also. Okay, so if you want to add an electron to oxygen and if you want to add an electron to sulfur, okay, where it is easy to add an electron, it is easy to add an electron to sulfur rather than adding an electron to oxygen. Why? Because again, oxygen is a small atom. Okay, when you want to add an electron, there will be more repulsion. But okay, as you go down, size increases, isn't it? As the size increases, the repulsion will be less. There will be less repulsion. Hence, it is easy to add an electron to sulfur rather than adding an electron to oxygen. Okay, I hope you understood. Okay, yes, this is the only exception. Please note this point. Okay, you should always, okay, find an exception only in case of oxygen and sulfur, okay, fluorine and chlorine. Okay, so it should increase, electron affinity should decrease from oxygen to sulfur, but actually it increases. Here also, okay, electron affinity should decrease from fluorine to chlorine, but actually it increases. So sulfur has more, okay, electron affinity than oxygen. Chlorine has more electron affinity than fluorine. But okay, halogens have more electron affinity than oxygen family. So what is the correct answer? Yes, so chlorine has more electron affinity than fluorine. Fluorine has more electron affinity than oxygen family, isn't it? Okay, that is sulfur. Sulfur has more electron affinity than oxygen. It goes in zigzag manner, just like this. So chlorine has more electron affinity than fluorine. Fluorine has more electron affinity than sulfur. Sulfur has more electron affinity than oxygen. Okay, halogen family will have more electron affinity than oxygen family. Understood? Among Halogen family, which has more electron affinity, it is chlorine. Among oxygen family, which has more electron affinity, it is sulfur. So the correct order is chlorine has more electron affinity than fluorine. Fluorine has more electron affinity than sulfur. Sulfur has more electron affinity than oxygen. So what is the correct option? The correct option is going to be option A. Is it correct? Chlorine more than fluorine, fluorine more than sulfur, sulfur more than oxygen. Hence the correct answer is option A. Yes, exactly. Okay, any doubts with this? Okay, can I continue? Yes, that's great. Yes. Okay, next question. Which of the following oxides is neutral in nature? Okay, which of the following oxides is neutral in nature? Okay, yeah. So remember one thing. See, oxides. Yes, oxides can be acidic. Yes, oxides can be basic. Yes, oxides can be neutral. Okay, oxides can be amphoteric. Amphoteric. Understood? Yes. So oxides can be acidic, oxides can be basic, oxides can be neutral, and also oxides can be amphoteric. Am I correct? Okay. See, always metallic oxides are always basic in nature. Metallic oxides are basic in nature, whereas non-metallic oxides are acidic in nature. Non-metallic oxides are acidic in nature. Metallic oxides are basic in nature. Non-metallic oxides are acidic in nature. Whereas certain elements like, okay, yes, tin, yeah, lead, yes, so these elements, they form amphoteric oxides. Sorry, okay, yes, okay, yes, it is tin, lead, zinc, aluminium. Okay, these elements, they form amphoteric oxides. Remember it, direct question. Okay, tin, lead, zinc, aluminium, they form what type of oxides? Amphoteric oxides. Metallic oxides, they form basic oxides. Acidic oxides, they are formed by non-metallic oxides. Non-metallic oxides are acidic, metallic oxides are basic, whereas these elements will form what type of oxides? Amphoteric oxides. Okay, only carbon monoxide is a neutral oxide. Carbon monoxide is a neutral oxide. Look at here, strontium oxide. Strontium is a metal, it's a metallic oxide. So metallic oxide means it is basic in nature. Carbon dioxide, carbon is a non-metal, therefore it's a non-metal oxide, non-metallic oxide, hence it is acidic in nature. Acidic in nature. I told you carbon monoxide will form what type of oxide? It's a neutral oxide. Whereas aluminium oxide, tin, okay, tin, lead, zinc, aluminium will form what type of oxides? They form amphoteric oxides. Amphoteric oxides. Understood? Okay, remember this. Metallic oxides, basic. Non-metallic oxides, acidic. Carbon monoxide, neutral. Okay, tin oxide, lead oxide, zinc oxide and aluminium oxides are amphoteric in nature. So which of the following oxides is neutral? Yes, obviously it's going to be carbon monoxide. The correct answer is carbon monoxide. Yes, excellent. Okay, yeah. Next question. Okay, just a minute, I'll turn off the fan. Yeah. Okay, next question. There are many elements in the periodic table which exhibit variable valency. This is a particular characteristic of what? There are many elements in the periodic table which exhibit variable valency. This is a particular characteristic of representative elements, transition elements, noble gases, non-metals. What do you mean by representative elements? Okay, S block elements and P block elements. S block elements and P block elements, they are together called as what? Representative elements. Okay, whereas D block elements are called as transition elements. They are called as transition elements. F block elements are called as, yes, okay, inner transition elements. Okay, so there are many elements in the periodic table which exhibit variable valency. What do you mean by variable valency? What is variable valency or variable oxidation state? Variable valency or variable oxidation state? Variable oxidation state. Look at sulfur. Sulfur can be, sulfur can have a valency of 2, 4, 6, isn't it? Okay, sulfur can be in +2 oxidation state, sulfur can be in +4 oxidation state, and sulfur can be in +6 oxidation state. This is called as variable valence. The same element, if the same element, okay, exists in different oxidation states, okay, if the same element has different valencies, then we call it as variable valency or variable oxidation state. If the same element exists in different oxidation state or different, okay, valencies, then it is called as variable valency or variable oxidation state. For example, iron. Okay, we know iron can be in +2 state and +3 state. Okay, we have Fe2 plus and Fe3 plus. This is what we call variable oxidation state. Okay, yes, that's correct. Variable, did you understand what is variable oxidation state? If the same element has different, if the same element exists in different valencies, okay, then it is variable valency. If the same element exists in different oxidation state, then it is called as variable oxidation state. Well, variable valency or variable oxidation state is a characteristic of which group elements? See, look here. So I told you, we know S block elements has two groups, alkali metals and alkaline earth metals. All alkali metals will be in +1 oxidation state and all alkaline earth metals will be in +2 oxidation state. No S block elements will have variable valency. Okay, all the alkali metals will have +1 oxidation state and all the alkaline earth metals will have +2 oxidation state. They will not be in variable oxidation state or they will not have variable valency. They have only they have only one valency. The valency of alkali metals is 1 and the valency of alkaline earth metals is 2. The oxidation state of alkali metals is +1, the oxidation state of alkaline earth metals is +2. Okay, they exhibit only one type of valency. Okay, they do not exhibit variable valency. Then variable valency, okay, now some elements of P block, they exhibit variable valency, no doubt in it. But okay, majority of the D block elements, more than 90% of D block elements, they exhibit variable oxidation state. Remember, only some elements of P block exhibit variable oxidation state, but more than 90%, okay, that means majority of the elements in D block, they exhibit variable oxidation state. Moreover, remember, variable oxidation state is a characteristic feature, variable valency is a characteristic feature of D block elements, that is nothing but the transition elements. Did you understand this? So there are many elements in the periodic table which exhibit variable oxidation state or variable valency. This is a particular characteristic of, it's not the characteristic of representative elements, that means it is not about S block or P block. Yes, it is the characteristic feature of transition elements, that is nothing but, okay, yes, option B, D block elements. Only the D block elements can exhibit variable oxidation state. Yes, so that's it. Okay, clear? Yes, next question. Yes, the question says, what is common between the cations and anions? Okay, we have oxide ion, fluoride, sodium ion, magnesium ion and aluminium ion. Okay, so what is common between the given cations and anions? They all have same ionic radii? Definitely no. All are isoelectronic species having 10 electrons. All of them belong to third period. Okay, all the nature of the oxides of all the ions is basic? No. Okay, so what is it? What is common? Okay, read out the question again. What is common between, okay, given cations and anions? We have oxide, fluoride, sodium ion, magnesium ion and aluminium ion. Okay, so oxide ion, fluoride ion, Okay, sodium ion, magnesium, aluminium ion and magnesium ion, isn't it? Magnesium ion and aluminium ion. Aluminium ion. Okay, come on. What is common? Okay, atomic number of oxygen is 8. Okay, that means only oxygen had 8 electrons, but upon adding 2 electrons, it will have 10 electrons, isn't it? Atomic number of fluorine is 9. On adding 1 electron, it becomes 10 electrons. Is it correct? Atomic number of sodium is 11. Okay, how did it get positive charge? Upon losing 1 electron. So sodium, upon losing 1 electron, okay, it will have 10 electrons. Atomic number of magnesium is 12. So magnesium had 12 electrons, but upon losing 2 electrons, the number of electrons is going to be 10 electrons. Correct? Okay. Aluminium, atomic number is 13. It had 13 electrons, but upon losing 3 electrons, the number of electrons is going to be 10 electrons. So that means all these ions, they have the same number of electrons. By the way, students, what do you call the species having the same number of electrons? The species with the same number of electrons are called as isoelectronic. They are called as isoelectronic species. The species having same number of electrons are called as isoelectronic species. Okay, so what is common? Yes. Okay, what is common between given cations and anions? Do they have the same ionic radii? No, they cannot. Okay, obviously anions have more ionic radii than cations. Okay, anions will have more ionic radii than cations. Therefore, option A cannot be the answer. All are isoelectronic species having 10 electrons. Yes, they are all isoelectronic species having 10 electrons. Obviously, option B is correct. Okay, all of them belong to the third period? No. Okay, oxygen and fluorine belongs to second period. Is it correct? They belongs to second period, whereas sodium, magnesium and aluminium, they belong to third period. Third period. Yes. So option C is also not correct. The nature of oxides of all the ions is basic. Just now I told you. Okay. Yeah. Metallic oxides are acidic. Sorry, metallic oxides are basic. Okay. Whereas non-metallic oxides are acidic. Well, oxides of fluorine and oxygen, they are non-metals. Therefore, they are going to be acidic. Okay. Whereas sodium, magnesium and aluminium, they are metals. Therefore, their oxides are going to be basic. Okay, even option D is not correct. Okay, the nature of the oxides of all the ions are basic? No. These two oxides are, these two will form acidic oxides, these three will form basic oxides. So even option D is incorrect. So the correct answer is option B. Option B. Understood? Yes. Okay, simple. Next question. Yeah, which of the properties of isotopes of an element is different? Which of the properties of isotopes of an element is different? Okay, is it the first ionization enthalpy, effective nuclear charge, electron affinity, melting point and boiling point? Isotopes, which of the properties of isotopes of an element is different? Okay, look here. Isotope, can we have some isotopes? For example, which are the different isotopes of hydrogen? The different isotopes of hydrogen are 1H1, 1H2, 1H3. Well, this is called as protium, this is called as deuterium, and this is called as tritium. Okay, look at here. They all have same atomic number. Correct? What is atomic number of protium? 1. What is atomic number of deuterium? 1. What is atomic number of tritium? 1. They have same atomic number. If they have same atomic number, means they'll have same, okay, they'll have same atomic radius, they'll have same ionic radius, they'll have same, okay, ionization enthalpy, they have same electron gain enthalpy, they have same electron affinity, sorry, electronegativity. Am I correct? Because, okay, they have the same atomic radius, sorry, atomic number. Okay, same atomic number means same number of electrons. Same number of electrons means same atomic radius, same ionic radius, same ionization enthalpy, same electron affinity, same electron negativity. Same electron negativity. Then what is different? Isotopes have different, okay, mass number. Okay, that means they are different atomic mass. They have different atomic mass. Okay, if they have different atomic mass, their certain physical properties will vary, like melting point and boiling point. Okay, I can say tritium will have more melting point and boiling point than deuterium. Deuterium has more melting point and boiling point than protium. Okay, since the mass number is different, they will have different atomic mass. Since their atomic mass is different, they will have different melting point and boiling point. But their atomic radius will be same, ionic radius will be same, ionization enthalpy will be same, electron gain enthalpy will be same, electron negative will be same. Simple? Okay, yes. So which of the properties of isotopes of an element is different? First, ionization enthalpy? No, they have same number of, okay, they have same atomic number. That means they have the same number of electrons. If the number of electrons are same, then all these properties is going to be same. Okay, so yes, first ionization enthalpy? No. Effective nuclear charge? No. Electron affinity? No. Then what is different? Yeah, they'll have different melting point and boiling point. Why they have different melting point and boiling point? Because they have different mass number, hence they will have different atomic mass. As the atomic mass varies, their melting point and boiling point will vary, their solubility will vary, their density is going to vary, etc., etc. Okay, therefore these isotopes, they are different. Okay, they are different with respect to what? Melting point and boiling point. Melting point and boiling point. Okay, simple. Okay, no doubts. Yes. Yes. Next question, students. Okay. Which is the most electropositive element? Which is the most electropositive element? Okay. Yes. So we have sodium, copper, cesium and calcium. Sodium, okay, copper, cesium and calcium. If you can arrange these elements according to the increasing order of atomic number, as it is there in the periodic table, you can get to know that sodium comes first, below which we'll have cesium, and then we'll have calcium, and then in the third period itself we'll have copper somewhere here, isn't it, like this? If you can just go back to the periodic table, you can understand sodium, cesium, calcium, copper. This is how it appears in periodic table. Look, you can have a look at the periodic table. You can just have a look at the periodic table. Yes, look at this periodic table. First we have sodium, and then down to it we'll have cesium, then we have calcium, is it correct? And in the same group as that of calcium, yes, cesium comes here, somewhere here, down to sodium, then calcium, in the same period as that of calcium we'll have copper. So the question is, what was the question? I hope you can observe sodium, below which we have cesium, yes, then calcium, in the same group as that of calcium we'll have copper. Yes, please arrange them according to the periodic table. Now what was the question? Yes. Which is the most electropositive element? See, rather than talking about electropositivity, let us talk about electronegativity. 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 We know along the period electronegativity increases. If electronegativity increases along the period, electropositivity will decrease. Is that correct? Correct. But down the group, as we go down the group, electronegativity decreases. It means electropositivity will increase. Correct. So which element is down? Which element is down? It is cesium. Is it? Okay, the element which is now at the bottom of the periodic table is cesium. Cesium is at the down. Okay, that means it has least electronegativity. If it has least electronegativity, that means it has maximum electropositivity. Correct? Okay. Hence, which is the most electropositive element? It is obviously cesium. Cesium is the most electropositive element. You have to go in this way. Okay. Along the period, electronegativity increases. If electronegativity increases, electropositivity will decrease. Down the group, electronegativity decreases, but electropositivity will increase. So, which element is at the bottom of the periodic table? It is cesium. So, cesium has least electronegativity, but maximum electropositivity. Hence, the correct answer is going to be, it is option C, it is cesium. Okay, yeah, that's great. Yes, next question, students. Okay, what is the next question? The main reason for showing anomalous properties of the first member of a group in S block or P block is, okay, what is the main reason for anomalous properties? That is the question. Okay, what is the main reason for anomalous property? I told you, okay, I have told you in the very beginning. Okay, you should stress on anomalous properties. Okay, so what do you mean by anomalous property? What is anomalous property or anomalous behavior? What is anomalous property or anomalous behavior? See, okay, the first element of each group will have properties that are different, okay, from the other elements of its own group, okay. This is what we call anomalous property or anomalous behavior. See, understand, students, the first element of each group will have properties that is different from the other elements of its own group. This is called as anomalous behavior. For example, if I go with the same periodic table, we have to again just go back, okay, to the periodic table. Understand this. So, okay, we have got different groups. Let us just concentrate only on S block and P block, because the question is basically on S block and P block. Okay, so we have got first group, second group, okay, 13 to 17 group in S block and P block. So which is the first member of lithium? First member of group 1, it is lithium. Okay, the second member of the first member of second group is beryllium. The first member of the 13th group is boron. Okay, the first member of 14th group is carbon, and then nitrogen, then oxygen, and then fluorine. See, these first elements, they have properties which are different from the other elements of same group. Okay, we know elements belonging to the same group should have same properties, same physical properties, as well as what? Same chemical properties. If the elements belong to the same group, then those elements belonging to the same group should have same physical properties and also same chemical properties. That means lithium should have the same physical and chemical properties than the other elements. Beryllium should have same physical and chemical properties than the other elements in its group. But lithium has different properties than other alkali metals. Beryllium has different properties than other alkaline earth metals. Boron has got different properties. Carbon has got different properties. Nitrogen has got different properties. Like that, oxygen and fluorine will have different properties from the other elements of its own group. This behavior is called as anomalous behavior. Okay, what do you call this behavior as? It is called as anomalous behavior. Okay, so lithium shows anomalous behavior in alkali metals. Beryllium shows anomalous behavior in alkaline earth metals. boron in boron family, carbon in carbon family, nitrogen in nitrogen family, oxygen in oxygen family, and fluorine in fluorine family will show different properties from the other elements of their own group. Okay, what do you call this property as? This property is called as anomalous behavior. Now the question is, why lithium is different, why beryllium is different, why boron shows different properties? Okay, like that, why carbon, nitrogen, oxygen, fluorine, okay, they show different properties. Why do they exhibit anomalous behavior? What is the reason for anomalous behavior? Okay, what is the reason for anomalous behavior? Why do they exhibit different properties? Okay, the reason for anomalous behavior is, we have got so many reasons, out of which, okay, yes, small size, okay, high ionization enthalpy, okay, high electron gain enthalpy, and non-availability of d orbitals. Okay, these are the reasons for the anomalous behavior of the first elements in its own group. Okay, what are those reasons? That is small size, high ionization enthalpy, high electron gain enthalpy, and the non-availability of d orbitals. So these are the reasons for anomalous behavior of the first elements of each group. Okay, yeah, let us go back to the question now. Yeah, the main reason for showing anomalous properties of the first member of a group in S or P block is, okay, is it because of maximum chemical reactivity? No. Is it because of maximum electronegativity and different configuration? No. What is the reason? It is because of small size, okay, high ionization enthalpy, high electron gain enthalpy, and non-availability of d orbitals. And also you can add one more reason, that is large, okay, charge to radius ratio, large charge to radius ratio. Okay, because of large charge to radius ratio, you can add one more point, that this is what we call, okay, high polarization power, charge to radius ratio. Charge to radius ratio, this ratio is called as, okay, polarization power. Polarization power. Okay, what is polarization power? Charge to radius ratio is called as polarization power. So the first element of each group will also have high polarization power. So because of all these reasons, the first element of S block or P block will have different properties, and that is called as anomalous behavior. Hence, what is the correct answer for it? Yes, it's option C. Small size, large polarizing power, high ionization enthalpy, high electron gain enthalpy, and non-availability of d orbitals. Yes, okay, correct. Yes, we shall move on to the next question. Okay, the next question says, why do noble gases have positive electron gain enthalpy? I have already told you, I have already discussed about electron gain enthalpy and why, okay, noble gases have positive electron gain enthalpy. Okay, see, I told you, noble gases, okay, yeah, they have already stable electronic configuration like NS2, NP6. They have completely filled, they have completed their octet structure. Okay, they have completed their octet structure, they have, okay, stable configuration. Didn't I tell you that it is difficult to remove an electron? It is difficult to remove an electron, as well as it is difficult to, okay, difficult to add an electron. Okay, so it is difficult to remove an electron, as well as it is difficult to add an electron from the stable configuration. Since it is difficult, okay, electron affinity is positive for noble gases. Correct? For other elements except noble gases, electron affinity is negative. For other elements, electron affinity is negative, whereas only for noble gases, electron affinity is what? Positive. Why electron affinity is positive? Because it is very difficult to add an electron to a stable, okay, configuration. Which is that stable configuration? It is ns2 np6, which is being exhibited by noble gases. Yeah. Okay. Now read out the question. Why do noble gases have positive electron enthalpy? Okay. Why do noble gases have positive electron gain enthalpy? Is it difficult to add an electron due to high small size, or it is difficult to add an electron due to high electronegativity? It is difficult to add an electron due to stable configuration. It is difficult to add an electron due to high electron affinity. What's the correct answer? Yes, it is option C. It is difficult to add an electron due to stable configuration. And which is that stable configuration? ns2 np6. Yeah, that's the correct answer. Yeah. From the stable configuration, it is difficult to remove an electron as well as it is difficult to add an electron. Okay, when we are talking about electron affinity, we should talk about adding an electron. Hence, it is difficult to add an electron to a stable configuration. That is why electron affinity is positive. Okay, so the correct answer is option C. Option C. Understood? That's great. Okay, shall we move on to the next question? Yes. What is the next question? The question says, predict the formula of a stable compound formed by an element with atomic number 114 and fluorine. Predict the formula of a stable compound formed by an element with atomic number 114 and fluorine. So we have an element X, say A, we have an element A and the atomic number of this element is 114 and we have fluorine. So we should predict the formula of the compound formed between these two elements. Okay, we should predict the formula of the compound formed between, okay, the element with atomic number 114 and fluorine. By the way, what is fluorine? Fluorine is an halogen. What is the valency of halogens? Okay, halogens will exhibit a valency of 1, no doubt in it. Okay, then what about the valence of this element with atomic number 114? Yes, let us go back to the periodic table. Yes, look at this periodic table. Where do you find the element with atomic number 114? Okay, here, is it correct? And to which group it belongs to? Well, okay, the element with atomic number 114 belongs to 16th group. 16th group. Okay, yes, that means the element with atomic number 114, it belongs to 16th group. Okay, what is the valency of 16th group elements? Okay, yes, the valency of 16th group elements is 6. Okay, the elements of 16th group, the elements, oh, I'm sorry, okay, so this is 114, isn't it? Okay, so it belongs to 14th group. Yes, 14th group. It's a carbon family element. The element with atomic number 114, it's a carbon family element. So we know for carbon family elements, which is a 14th group elements will have what valency? They will have valency equal to 4. Okay, so what is the valency of this element? The valency of this element is 4. Okay, and fluorine has what valency? 1. Okay, so how do you going to write the formula of these two? How do you write the formula of this compound? Okay, formed from these two elements. Okay, very simple. What are you supposed to do? You just have to cross multiply. Is it correct? Okay, cross multiply the valency. When you cross multiply the valency, you will get A1 F4, or simply it is AF4. AF4. Is it correct? Okay, yes, let us go back to the question. The question is like this. Okay, predict the formula of the stable compound formed by an element with atomic number 114 and fluorine. So this belongs to 14th group, therefore its valency is 4. Fluorine, okay, yes, its valency is 1. Okay, therefore if you cross multiply the valencies, you will get AF4. Hence the formula of the stable compound is AF4. AF4. Understood? Yes, exactly. Okay, yes. Let us move on to the next question then. Okay. Students, we shall continue with these MCQs in the next video also. Okay. I hope you have understood. Okay. Thank you so much.